I don't know how far you guys are now in chemistry. I'm told that there's Mr. Mwanza taking you up in that field. So I don't know how far you guys have gone. However, with our discussion, remember what is ahead of us is the exam. So even as we discuss, we are discussing in readiness for the exams. So I will not have to wait. I will not have to wait until it's too much, until it's late. That's when we wake up and say, this we didn't do, this we didn't do. So we'll start touching we'll start touching many parts that are brought in an exam. So, and today's discussion is coming from extraction of metals. We will be looking at extraction of metals. Now, unfortunately, this part that I have brought, I have just extracted it from the middle of many things. However, I will guide you on certain information that you need to have for you to clearly understand extraction of metals. So let me write it here, extraction of metals. So the extraction of metals that we are looking at today, first of all, we can say that this is the method that is used to obtain pure and dry forms of metals from their impure form, which we call metal ores. So the extraction of metals is just a method. Different methods actually that we have that we use to obtain or to extract pure forms. And these pure forms must be in solid form. That's what I'm saying, dry samples or dry forms of metals. These metals are being extracted from their impure forms. The impure form is what we are calling metal ores. How best can we understand this? Let's look at meal. When we grow maize, we actually make a lot of things from maize. We do extract meal from maize. We do actually extract sample from maize. There are quite a lot of things that we do extract from the maize. So the meal that we see, the meal that we enjoy in our homes, these are some of the forms that we extract from the meal. But I'm not saying that meal is an impure form. No. I would say maybe the impure form of meal is when we harvest maize cobs. In those maize cobs, there we remove the outer part, we extract the grain, then we throw the other things. So different methods are used in the extraction of actually the maize, the grains from the cob. So the methods that we use to extract pure metals from their impure form, which we are calling metal ores, is what we are calling as the extraction of metals. So how many methods are there? How many methods are there? Basically, there are 3 methods. So there are 3 methods. Which methods are they? One is what is called reduction by carbon. The first one is called reduction by carbon. The second one is called thermodecomposition. The third one is called electrolysis. So these are the three methods that we are going to look at that are commonly used in the extraction of pure forms of metals from their impure forms. Three of them. Now, how would you know which method to use for a particular metal? I'll come and guide you that when we start looking at, actually it could have been the first part, but don't worry, the part that we're looking at today can fit even at the point where we are. I'll guide you on how to tell. So among these three methods that we have listed, today, the one that we are going to look at is this one, which is called reduction by carbon. And reduction by carbon, there are just three metals in our syllabus that we can extract using that method. The first one is zinc. Zinc can be extracted by that method. The other one is lead. The other one is, no, not lead. The other one is iron. Two, actually. These two are the ones that we can extract using reduction by carbon. So the same method that we're going to look at under iron is the same method that is used when you're extracting zinc. Can I have questions if there are people with questions? I'm saying there are three methods: reduction by carbon, thermodecomposition, and electrolysis. Now, because today we will be looking at reduction by carbon, that's why it was very important for me to indicate the methods that are extracted by that method. And those metals are two, the ones I've listed, zinc as well as iron. So you have to pay attention to the particulars, because once we look at iron, we will not look at zinc in details, because like I said, some properties or some steps are the same. Now, in the moment when we are talking about the impure forms, these impure forms of each metal are very important, and we have got names. So the first thing would be, what is the metal ore? What is the metal ore from which iron is extracted? There are three major metal ores. Which ones are they? You need to know their names. You need to know their chemical names as well as their chemical formulae. So the first one is called hematite. Now, this hematite is just some scientific name. The chemical name is called iron 3 oxide. And writing the iron 3 oxide in chemical form, this is how you can write it. So this is the first metal ore. The hematite, which is iron 3 oxide, the chemical formula is Fe2O3. The second one is called magnetite. The magnetite is almost the same as hematite. The only difference that we have is that iron has got a different valence. So this chemical formula that we have is called triiron tetraoxide. Tri means 3. How many are 3? Iron, that's why we have got 3 of iron. Tetracycline, tetra represents the number 4. Which ones are 4? Oxides. So we can even see that, okay, there are 4. So triion tetraoxide is the chemical name for magnetite. 3 of iron atoms, 4 of oxygen atoms. It is like from the hematite, we have just increased each atom by 1. We had 2 iron, you have got 3 iron, you have got 3 oxide, here now you've got 4 oxide. That's how easy it is for you and me to remember. The other one is what is called siderite. Siderite, I don't know how you can pronounce it in your own way. This one is different. It's not iron with oxygen, it's iron with carbonate. So it's iron 2 carbonate. So this iron is what makes it impure. What makes all these to be impure because of these things that are added. Here we've got the carbonate, here we've got the oxygen, 4 of them, here we've got oxygen, 3 of them. So the combination of these two make them not to be pure entities. However, when we're in homes, we're trying to make some tea. Someone is requesting for the notes. I'm going to send the pamphlet, the entire pamphlet with you guys. Because for me, this pamphlet now is not been useful. I'm now handling pure, so I can definitely share with you. So when you are in homes, we're trying to prepare a meal. Let's say shima. For me, that's what I call a meal. These other things, it's not even food. Yeah, they are just additives. You may have mini meal extracted from maize. You may have mini meal extracted from millet. You may have mini meal extracted from sorghum. I've eaten those things before. Now, when you have those 3 things, you may have preferences. Which one would you prefer to prepare? Now, for these 3 metal ions that we have, metal ores that we have, there are definitely only one that we call the chief metal ore. This is called the chief metal ore. And the chief metal ore here, they like asking this question. It's hematite. The hematite is the one that we use even in Zambia. When we say there's a mine where we extract iron that Kafue Steel processes, as well as these other companies making burger bars, making window frames, making door frames. The one that they use is hematite. Why do we use a hematite? Because it's the one that is commonly found. And actually, for our own information, Congo has got a larger percentage of certain metals compared to Zambia, and Zambia also has the larger percentage of other metals compared to Congo. But gladly, Zambia, we're a very peaceful country. In Congo, there are a lot of wars as they fight for these minerals. So we should continue being a peaceful country. So the metal ore that we use, the chief metal ore is hematite, which is iron 3 oxide. Now, every now and again, I'll be talking about the chemistry in the kitchen. Because when we are preparing a meal, let's say dad, mom says, prepare supper for your friends. Let's say you are trying to prepare shima. There are a lot of things you're going to need. You need water, you need heat, fire, you need meal, you need the cooking stick. There are quite a lot of things that we need. And during our extraction, what are the things that we need? What are the things that we need? The things that we need is the metal ore itself. The metal ore must be there because that is where we need to extract our iron. So the metal ore, which is hematite, must be there. What else do we need? We need calcium carbonate. We need calcium carbonate. But at times they just call it limestone. But we understand chemically that limestone there's calcium carbonate. It must be there also. Remember, when you are done cooking at the end of the day, you need to clean the pot. So actually what helps us in cleaning the chamber where we do the extraction is that hematite. What else do we need? We need coke. Now this coke is just, at times they call it charcoal. We need charcoal, but they don't say charcoal, they say coke. At times you can just say carbon. So these are the three things that you need. They like asking this question in an exam, and conclusively, these three things have got a name which is called charge. So the combination of hematite, limestone, as well as coke, it is called charge. So these are the three things that you need for you to do the extraction of iron. So this is what happens. Now, during the actual extraction, what really happens? Now, these three things, by the way, you need to know that each one of these has got a role to play. So this one has a role to play, this one has a role to play. Just like cooking, meal has got a role to play to solidify, to make that action shimmer. You need a cooking stick to do the mixing of water and meal, the stirring part. You also need heat so that the bond between water and meal can be strengthened. Remember, when you just get cold water, you add meal there, you stir, you stop stirring. They don't really mix, making something better. You see, now when you heat, the bond are strengthened. So those are the things that we use in our cooking and in our extraction. Each one of those has got a role to play. So let us see what really happened. Can we have questions for now? Are there questions? Yes, Trisha.
So for the chief ore, the hematite, calcium carbonate, and coke, why are they called the charge?
Why are they called charge? Basically, what happened is that, it's even here. These three things are called charge. What happens is that they are all loaded at the same time in the hematite. It is maybe because I'm trying to answer it from my own understanding. I've never come across a theoretical point. What really happens here is that all these things are charged within this thing here that we have. They're actually loaded at the same time. Perhaps that could be the reason as to why they are called charge. But should there be any other reason? Should there be any other reason, I'll definitely communicate to you in due course. Yeah. Should there be any other reason that might emerge, I'll definitely communicate in due course. But the only information that is there in your syllabus is that it's given a name chart, but they have not really given a full explanation why it is like that. But according to my own understanding, that because they are charged, they are loaded within this thing at the same time. Any other question? The other thing that we have to understand that when we are doing the cooking, there are a lot of kitchen utensils that we have. We have spoons, we've got fork, we've got different things that we have in the kitchen. But when doing the cooking of shima, unless you've just run out of options, that's when you can use a pan. we use pots. So even in our extraction of iron, we may have a lot of things there, but the thing that we use here has got a name. And the name of this thing is called the blast furnace. So the name blast comes from the guy who invented this thing. Remember, in science, we like giving honor we like honoring people who have done much of research. We have in electricity, the other day we were talking in magnetism. I don't know if you guys have looked at it. We've got Faraday's law, we've got Fleming's right-hand rule, those things that are beginning, the Flemings, the Faradays, the Lenzes, the Isaac Newtons, all those are the names of people who discovered. So the guy who invented this has got a name, Blast. Now, when you look at the Bible, I remember you, all of you, I'm sure, are Christians. The three Hebrew children, Shadrach, Meshach, and Abednego, I'm also a bit of a Christian guy. They were thrown in a fire furnace. So in that furnace, what was there was fire, and mostly the word furnace is associated with heat. So because the guy who discovered this is Blast, and then he used the heat to do his demonstration, and that's how the name was given as blast furnace. So the blast furnace is the name of a very huge chamber or a tower where the extraction is done. And the research reveals that it's a very big thing, actually, 30 to 40 meters of height. It's quite huge. Now, this thing, we don't just use any jim and jack that we find. Remember, even when you are doing the cooking, the selection of the instrument that we are going to use, remember we are putting that pot on the heat. So meaning the melting point of that pot actually should be higher than the heat that it is subjected to. Otherwise, the pot will melt. So what are the things that this Blast guy worked on when he was making this thing? We are saying it is made out of steel, because steel, remember, it's an alloy, and the reason as to why we make alloys in order to increase the durability, the strength, and many more of the properties that pure metals show. So steel actually is made of carbon as well as iron, physically combined to make an alloy we are calling steel. So it's made out of steel in order to make it strong. And they're saying the line is made of fireproof bricks. So the lining around here, there are bricks that do not really absorb much of the heat. Because if a lot of heat is absorbed here, you find that the entire thing will become heated up, and people around here may not even come near near this machine. But we're saying that every now and then this machine should be loaded with charge, because the extraction is an ongoing process. And not only that, if that doesn't happen, you find that this thing can melt. So the only way we can prevent the melting is that this machine here should have got a high melting point. So they do ask questions to say, what are the physical properties of a blast furnace? It must have high resistance to heat. It must be made with high melting point. Not only that, it must also be of high density. Remember, if this thing is very light, you load this thing with what we are calling charge, and the temperature here go above 500 degrees, above that. So now, in case this thing is not of high density, chabwela chagwa, if it falls, remember we can have disaster around. So we need to make sure that all that is prevented by increasing the physical properties of this object. Now, let us try to look at each and every part which is there. What does it do? Steps now are written down here, but allow me to write them up so that you are able to follow with a diagram. Steps are written down there, but I don't want to scroll down. I want to do right from this diagram. Unless there are questions. Are there questions? Steps or procedure, and this includes chemical reactions. So the first thing that starts the chemical reaction is limestone. So the limestone decomposes. Now remember, decomposition only happens when a substance is heated. Decomposition. When the body, let's say a dog is bashed, it's thrown by the roadside, the body will decompose because of heat. But when you get that dog, you go to Congo where they eat dogs, then you put that dog in the fridge. The decomposition actually may take longer. So the decomposition of limestone here, we are saying, is because of heat. And remember, limestone is calcium carbonate. So what happens here is calcium carbonate, CaCO3. So even if you're not writing these notes, remember I'm going to share with you this pamphlet. When it decomposes, we are going to form calcium oxide plus carbon dioxide. Oh, sorry. I don't know where my mind is. This is the second last equation actually. What starts is not the decomposition of calcium carbonate. Forgive me, I don't know, I might have gone somewhere. What begins is coke. Coke reacts with the oxygen. Now remember the reaction of a substance with oxygen, actually what that is called is burning. So coke burns. And when it burns, what is formed is carbon dioxide. So this is the first reaction. Allow me to ask for forgiveness. So the first thing is carbon, which reacts with oxygen. What is formed is carbon dioxide. Remember, we are saying the method is reduction by carbon. So we need to have a substance which is going to make the reduction process possible. This is the first reaction. This reaction is very important. Why is it important? Because this carbon dioxide which is used, we are not throwing it. We'll come and use it again. So this carbon dioxide which is produced is the one that they're calling a blast of hot air, which is pumped back into the chamber. Remember, it's a gas. The gas can escape. It goes as a waste gas. But waste as it may be, it is collected somewhere and part of it is pumped back. And why are we doing that? Remember, this carbon dioxide which is produced from a burning, it's hot. So if we allow it to escape, the temperature in here will not be good for the decomposition of calcium carbonate, because for calcium carbonate to decompose, the temperature has to be high. That's the first reaction. The second one, this carbon dioxide which is produced, it reacts again with carbon. So carbon, coke reacts with the carbon dioxide. And what is formed here is carbon monoxide. So carbon monoxide is produced. And this carbon monoxide which is produced is very, very important in our execution. Actually, this carbon monoxide that we have here is the one that is responsible for the process of reduction to be completed. This is the guy who does the actual reduction. The method is reduction by carbon, And the guy who does that reduction is Mr. Carbon monoxide. Therefore, we will give him a very scientific name that he is a reducing agent. So this guy will be called a reducing agent. He is an agent who is trying to make sure that the process of reduction is actually done. Remember, MTN, Airtel, and Zanaco agents, these are the ones who open accounts for us so that the saving can be enhanced. So for reduction to be there, the carbon monoxide should be there, and he is called a reducing agent. How best can we show this? It's carbon reacting now with carbon dioxide, and what we are forming is a reducing agent, which is carbon monoxide. So definitely you can just put a 2 here so that our balancing is done. Now, when this guy who is a reducing agent is produced, we are saying that now the process can even begin, because the guy we've been waiting for is finally here. So the third point now, it's now the actual reduction. And they like asking this question. So now it's a reduction of hematite to pure iron. We have done the extraction. It's done. It's done, dusted. So we are saying that the guy who does this process is because of the production of carbon monoxide. So if carbon monoxide was not produced, this process was not even going to be possible. So let us show how that is done. So we start with hematite. Remember, hematite is Fe2O3. Once we increase by 2 or by 1 atom, Fe2 or Fe3O4, it changes to the other metal. So this reacts with carbon monoxide. Now, when we use the word reduction, what it actually means with respect to this equation is that iron is going to lose oxygen. Remember, even in life, there is that friend that you have, that once you are separated from that friend, you have been reduced in some aspect. So oxygen is that good friend to whom whoever loses him, it becomes reduction. So, and the guy who is going to get this oxygen is this guy. That's why we are calling him an agent of reduction, because he's the one who's removing oxygen from the iron, making iron to be reduced. Yeah, okay, let me tell you one thing. You guys being away from me, maybe it's a bit of a reduction on my side. I haven't yet made friends like you guys were. You're very good friends to me. But anyway, it's not really a reduction as in per se, because you guys and I are still interacting in one or the other, though we are not meeting like we used to. So now when this happens, we are saying what is formed is now pure iron plus carbon. Now, do not put there's 1 here plus this 3, we put carbon with a 4 here. No, what is formed actually is carbon dioxide. All you need to do is just to balance up the chemical equation. And our balancing will mean putting a 2 here. When we put a 2 here, oxygen will be 4. Yeah, oxygen will be 4. 4, yes, oxygen is 4 already, and then the iron, we have got 2 here, we'll just put a 2 here, and this will be the balancing of the equation. So the extraction is done because the pure form of iron has been formed. The pure form has been formed. So all this happens within this chamber. Now, the moment we are coming to form iron, remember this iron is a solid. And when this happens, this iron here must be in molten state, must have melted. Now come to think of it, at what temperature will it be for iron to melt? So in here, it's very hot, super hot. That's why we have used the word furnace to refer to this chamber. However, this iron which is extracted here, the pure form of iron, can rust. Yeah, it can rust. That's why when you get a steel, when you get a wire nail, you leave it outside, it rains. The following day, you find there will be some reddish brown compounds which we call rust. So to prevent that, we'll look at methods of preventing iron from rusting. Now, when this happens, remember this iron is coming from, this hematite is coming from a soil, from the ground where there were a lot of impurities. And the major impurity here is sand, but that sand is called silicon. So the major impurity here is silicon dioxide. Now, silicon dioxide is actually an acidic compound. So the only way we can remove that acidic compound from this blast furnace as we make it ready for other use is that we must introduce a base. So here we have looked at where coke is used. We have also looked at where the hematite is used. The only thing remaining here is now limestone. So this limestone has to decompose. This is number 4, or the 3 was here. So this is 4. So now what happens here is the decomposition. The one that I made a mistake by putting it on top, decomposition of iron. No, of limestone. So the limestone actually decomposes. And the equation is the one that I written at first. Calcium carbonate decomposes to form calcium oxide plus carbon dioxide. Gosh. Now, come to think of it, how many times have we produced carbon dioxide? Just how many times? You can count. 1 here, it is produced. 2 here, it is produced. 3 here, it's also produced. So that's why I'm saying this gas, we can't throw it. It must be pumped back into the chamber as a hot air in order to preheat the blast furnace, also so that it can come and react with coke in order to produce the reducing agent. So there are 2 reasons that I've given you. We are saying we cannot let go of it completely. We need to pump it back into the chamber so that 1, it helps in maintaining the heat in the system. Secondly, it also helps in reacting with carbon to form, remember our method is reduction, and the guy who is doing that is Mr. Carbon monoxide, who is only produced when carbon reacts with carbon dioxide. So if we completely eliminate carbon dioxide from this chamber, then the process at some point will have to stop even before the other hematite is extracted. Now, so we know where this goes. What about this calcium oxide? This calcium oxide, now it's number 1. Calcium oxide reacts with silicon dioxide. So calcium oxide reacts with silicon dioxide to form calcium silicate, which is a complex, a bit of a delicate compound. So we are forming calcium silicate. How is it done? So we have the calcium oxide here, and actually, this is the last one. Calcium oxide, which is reacting silicon dioxide. What we are forming is calcium silicate. So calcium here, silicon here, and oxygen. So 2 plus 1, that is 3. This is silicon, this is calcium silicate. Unless there's something wrong with my valences, let me just check it out. Calcium silicate. I was right, it's already here. This is our calcium silicate. It's already here. This is the one that we have here. Now, this calcium silicate is actually an impurity. This calcium silicate is actually an impurity, and it is known as slag. So there are two things that we will obtain from the blast furnace at the end of our experiment. One, this iron here is in molten state, it's not solid. This calcium silicate is also in molten state. So we have two major things we are going to obtain from this blast furnace at the end of the experiment. We are going to have calcium silicate slag as well as molten iron. But we need to understand that this molten iron is heavier and therefore it will sink at the bottom of the blast furnace. So how can we see it? Let's look here. We are saying the molten iron, which is heavier, must sink at the bottom. Then the molten slag, calcium silicate, which is lighter, will sit here. So this is calcium silicate, and this is molten iron. Then this is extracted, and that is also extracted. But when you throw this impurity molten slag, you just get it, you don't throw it, because it has got the uses. And these uses will come and discuss them later when we start looking at this molten iron that we get. Where does it go? What uses do we have for it? Then we'll also come and look at the uses that we have for slag. So this slag actually removes the collection of all the dirty things that were around this to come and remove it as impurities. At that point where I was saying, when you are done cooking, you don't throw the pot and go and buy another pot that you're going to use for cooking. No. So that is how it is done. So unless there are questions, please ask me. Otherwise, for me, this is okay. I will send the notes, I will send the work. But for now, can I have questions, please?
It's clear for me. I don't have any questions.